Hello and welcome back, everyone. This is our third and last day of EnzymeCon 2024. It is still organized by the same people, you would not believe this. And we have a shorter program today. We only have one session in the morning, and in the afternoon we have a lot of time for hacking and free-form discussion. I think we'll merge that with lunch if some people want to go for lunch. Anything we should say before people start checking their email or listening to talks?
I think that's basically it.
Okay, so please pay attention to talks. We still have 4 talks. They're great. We scaled them on this day because we have... we had a third day. We had to schedule somebody. These are great. So let's start with our final session on applications. And our first talk is on AD on the IPU with EnzymeGL by Mose.
Okay, hello. I am Mose, and before starting, I wanted to acknowledge the people who helped me in this work. This includes also Valentin for the GPU compiler work, and also Emily and Luke from Simula, who started actually this project. I picked it up at a later stage, and my colleagues in UCL, including Owen, Sophia, and Matt for their help with preparing also these, the exams that I will show. And also people in GraphCore, because they helped me with figuring out how to use it, the IPU. So what's the IPU? The IPU, it's an accelerator. You can think it's similar to the GPU, but I will make some comparison with the GPU later, but the details are, it is the first wafer-on-wafer processor. Each of these chips has 0.9 gigabytes of memory with a bandwidth of 65 terabytes per second. It has 1,472 independent processing cores. Each of them actually can run 6 threads in parallel, so for a total of almost 9,000 parallel threads on each chip. And usually this chip come on board in a single board of 4 of these IPUs, so in total you get 3.6 gigabytes of memory for 260 terabytes of per second of bandwidth, and in terms of petaflops, I think this is expressed in half precision, and it's 1.4 petaflops of compute. Yeah, so this is a zoom in each of these IPU. You can see there's a grid of, they call them tiles. So each processor is called tiles. So they have, again, 1,472 tiles. And yeah, here are pretty much the same numbers that I showed before. Some comparisons with CPU and GPUs. The main striking difference is that the IPU uses multiple instructions, multiple data. So each core can run a different stream of instructions instead of doing the same on all the cores at the same time. And so you can also have programs that are more complex because, again, each core in parallel can do different things. Yeah, you can see here the other differences, but I think the paradigm, the multiple instructions, multiple data is the main outstanding feature of the IPU. Some other comparison, technical comparison with the GPU. This is A100, which by now is a bit old. So yeah, you can see here the number of independent streams. For the IPU, it's almost 9,000. For the A100 was about 7,000. The SRAM per core is 600 kilobytes per tile on the IPU, and it is about 192 kilobytes per for the A100. And also the memory per tile per register is about 100 kilobytes for the IPU and 7 kilobytes for the A100. In terms of vectorization, the IPU has 2 floats. Instead, the GPU can do 32 floats, so it's a smaller register. And in terms of peak or teraflops per second, it's pretty much similar to the A100. How you program the IPU? The company which builds the IPU is called GraphCore, and they provide an SDK called Popla with the functionalities to interface the low level of the IPU, and then you can also build like you can write your kernels in C++. It's not like a different dialect; it's just plain C++. But you need to use the functionalities provided by the Poplar SDK. But if you want to do more high-level stuff, you can use the GraphCore implementations, so for example, PyTorch and TensorFlow. But these are domain-specific, so these are only for basically machine learning. And this is here instead a schematic of how you can program an IPU. So each tile can get different streams of data and do something, and then you have the vertices, which are like the kernels that are being run, and they can be in principle different. So each vertex can be a different operation, and then you can stream the data that comes out of each kernel into some other operations, so some other kernels, and you literally build a graph of operations. So that's why also the company is called GraphCore. But why this is relevant for us? Because the GraphCore compiler that they use for the IPU is built on top of LLVM. And so what we did was to create a Julia package which uses the GPU compiler.jl framework, which is the same used also by Enzyme, to generate the LLVM IR of the functions that we want to run on the IPU. We write literally in a file, and then we use the Poplar compiler to generate the native code for the device. So all in all, this package does interfacing with the Poplar SDK, so you can use not all of them, but most of the functionalities in the Poplar SDK to access the low-level functionalities, but also use Julia metaprogramming capabilities to simplify how you program an IPU, and also the code generation to be able to write generic high-level code in Julia and be then compiled for the device natively. So this is a quick schematic of what we do. So we write code on the host. We use GPU compiler to generate the LLVM IR. And use the POPC. POPC is the Poplar compiler to generate the native code for the IPU, which then can run on the device. Yeah, so again, we used this GPU compiler framework to build this pipeline. There are some limitations, like all the code has to be statically inferred. You cannot use any functionalities which require the Julia runtime, most notably the garbage collector, and cannot use external libraries like BLAS libraries. And also did some quick experimentation with using the GraphCore LLVM fork, which exposes the backend. So I could generate directly the code optimized for the IPU backend. This kind of works. There are some problems, but it was an interesting experimentation also to use a new experimental backend from Julia. Okay, so now let's see how to write some code for the IPU. You can use this IPU toolkit package. So all the code that you write for the IPU, at least the one that I will show is very verbose. So don't be scared, I will show lots of code. But here the interesting bit is this one is a kernel. So this is to compute pi using like the integral of 1/1 plus x squared. So some numerical integration. And also a caveat is that this algorithm is very bad in single precision, so you will see very inaccurate values of pi, but this was not the point of this exercise, it was more doing some number crunching. So yeah, we are, with this at Kotlet macro, we are defining a kernel that will run on the IPU, and then we dispatch to all the tiles, so we are going to parallelize this computation over all the tiles, and get the result out, and the result is that by using all these tiles, which are all of them for the IPU, we got this value of pi, which the first 3 digits are okay, the rest is not good, but again, don't worry about this. And it took to run 0.12 seconds on the APU. Actually, there is some data movement between the host and the device, which takes much longer than these 0.12 seconds. But on the host, the only number crunching took this long. I also did a comparison with an equivalent C++ program. This is the kernel written in C++. The kernel is pretty much doing the same number, the same kind of computations. The interesting bit is that, okay, the result is not good. I think there are some problems with the additional, like doing the summation is, okay, don't worry. But point is, the time that it took to run is pretty much similar to what we got with a Julia kernel, with the kernel written in Julia. It's actually, in this case, slightly slower. I believe it's just a matter of loop unrolling. Somehow Julia, in this case, was doing better loop unrolling than the C++ compiler. But yeah, it's, my point is, we are very close to what you can get by writing the native C++ code. So I think this was a showcase that Julia can be a good front end for writing code for the IPU. But here we are at EnzymeCon, so we need to talk about doing some stuff with enzyme. I implemented, so this is a Rosenbrock function. I guess many people are familiar with it. It has this shape. So it has this valley, which is very interesting because it's very close for a minimization routine to get into the valley. The hardest bit is getting to the global minimum, which is this spot here in 1.1. And so we wrote a Julia program to minimize the Rosenbrock function. But what we wanted to see is how many iterations it takes to get to the minimum. So this is a add-on implementation, which is, again, returning the t, which is the iterator, the number of iterations that this routine is doing. And we are passing somewhere, yes, here, the derivative of the function. Derivative, which we are computing with enzyme. So this is the autodiff deferred is a enzyme function. So we will pass the Rosenbrock derivative computed by enzyme. So here are preparing the program, preparing the grid of points where I want to run this minimization on. And scroll down, scroll down, scroll down. Yeah, we get here. So this is a plot, which again is showing how many steps this program was taking to get to the minimum. So here in the valley, you can see the number of steps is very low. Of course, far from the valley, it takes much longer. And yeah, so this took in total 30 seconds to run on these 33,000 points. I think I tried to run on my CPU. It would have taken much longer. So this was also a good showcase that you can write these kind of programs and be very efficient on the IPU, taking advantage of the high parallelization. And if you're curious, here I also have the LLVM module that was generated by Julia. But another showcase of the using enzyme on the IPU is doing some Hamiltonian Monte Carlo. So Hamiltonian Monte Carlo means that you have an initial distribution of numbers that then you want to push towards another distribution, which is maybe harder to sample from. And you use the gradient to push the particles towards the target distribution. This is, again, a place where a autodiff engine is very useful. And so, again, I'm using enzyme for doing this. We start, again, from the Rosenbrock function. We prepare the Hamiltonian Monte Carlo. This is just how you would implement it on the CPU. This code actually runs as finals on the CPU. Now there is the program, again, super parallelized. And so we have here, our initial distribution is this interesting shape. I don't know if anyone knows it. And then we can go through, through the chains of the Hamiltonian Monte Carlo sampling, and we can see here that we were able to push the particles towards the minimum of the potential. And also, just for fun, I tried another potential. Instead of the Rosenbrock function, I tried another fancy potential, which has this shape that should appear in a few seconds. Yes, which may or may not have to do with the Julia logo, these three Gaussians. So again, we start from the initial distribution, which has this peculiar shape, and then we can go through the different samples of the Hamilton Monte Carlo and see that the particles have been pushed in these wells of potential that are basically a Gaussian shape. Yeah, it's interesting, the Hamilton Monte Carlo, because I wanted to showcase that you can use very loopy code and branches. There is no problem because the IPU, actually the way you write a IPU kernel is much closer to CPU rather than a GPU. So you can use whatever constructs you're used to use on a CPU. And that's completely fine. The last bit I wanted to talk about for the IPU is a stochastic rounding. Stochastic rounding means, so first of all, real numbers constitute a continuous set in R. But we know that computers use a finite precision, so they cannot represent all numbers in R, but they will use a basically subset F, a discrete set F, which is a subset of R. So when we do operations with floating point numbers, we basically get a result x hat, which belongs to F, not R, and so the results are actually the closest number in F to the actual number X that we would like to get in R. What computers usually do is to do deterministically rounding to the nearest number in F. But many people suggest using stochastic rounding, which means when you want to round your operations, you round with a certain probability, which means that you round down with a certain probability p or round up with a certain probability 1 minus p. There can be different choices of this probability function. One is p of x equal to 0.5, so half of the time you round up, half of the time you round down. But one more interesting probability is to round with the probability which is proportional to the distance to the nearest numbers in F. So sometimes you round up, sometimes you round down, but in this case you round more likely up because your true result X is closer to the X2, which is the upper bound in this interval. So why stochastic rounding is useful? Because on average, the results of the operations matches the expected mathematical result. And so in a statistical sense, they retain the information that is discarded by doing deterministic rounding. And this is very important when you use low precision floating point numbers, for example, half precision with 16 bits, or even think of the even lower precision floating point numbers that are being added to GPUs every time. I'm talking about this because the IPU is one of the very few processors available that have hardware support for stochastic rounding. There are many companies, including NVIDIA, who has patents about stochastic rounding, but they apparently don't have yet hardware implementations. So the IPU is actually the only one that I know, but I know there are very, very, very few systems that can do stochastic rounding. So just a very quick explanation of why stochastic rounding is useful. So you take the number 0.9 in half precision, you sum it 30,000 times, you expect the sum to be 2.7 thousandths. But if you do that, you actually, no, was here. Yeah, sorry. The result is 2048. The problem is that the number 2048 in half precision has a epsilon of 1, so the number 0.9 is lower than 1, and so when you try to add 0.9 after 2048, you're just adding 0 every time. Instead, we can do stochastic rounding and compute this sum multiple times on the IPU. And we basically get this distribution. So I did here with the program that I skipped. I summed this number up to 3,000, but repeating this exercise 100,000 times. So I get a distribution. And we can see here that with nearest rounding, you get always the same result, but it's always wrong. With stochastic rounding, you get different results, but statistically, they are neatly distributed around the actual result, which is 2,700. And here there are some statistics. So the extreme of this distribution are between 2,500 and 2,800, which is pretty much around the expected results, but none of them is 2,048. The mean is almost 2,700, and the median is actually exactly 2,700. Another showcase of using Julia on the IPU, there is no enzyme here, but I think it's cool to showcase what you can do with stochastic rounding. Is that I solved a differential equation on the IPU using a package called diffeq gpu.jl, which I was actually using on the IPU, but that was completely fine. I'm solving the Lotka-Volterra system, and then I'm solving this on the CPU using double precision and using this as a ground truth for the comparison that I'm going to show, and then also solving on the IPU using both nearest rounding, which is the default mode, and stochastic rounding. So we can see the result after all this code. So the green line is half precision stochastic rounding. Blue line is a double precision, which again we take it as the ground truth, and the yellow line is a half precision using nearest rounding. And you can see that with these parameters, nearest rounding is very, very much inaccurate, and instead stochastic rounding recovers all the precision that you lose by using a low precision floating point numbers. Can try different parameters. We can see that when it will show up. Nearest rounding in this case is not as bad, but still stochastic rounding is much, much closer to the actual real good result. So again, I think this was a cool showcase of how stochastic rounding is useful when you want to use low precision floating point numbers, which means you can use one quarter of the memory in this case, and maybe get 4 times the throughput. Conclusions, all over this work, I had lots of problems because apparently I was the first one to try some stuff using the LLVM backend for the IPU. But it was fun because it worked in the end. So as far as I know, this was the first third-party programming model for the IPU, not supported directly by GraphCore. And this was made possible by the ubiquitous LLVM compiler framework because it was used by the vendor and Julia and also Enzyme. Julia allowed us doing a general purpose programming using a high-level language, which is a programming model not available at the moment on the IPU. And Enzyme is a perfect match for running code on the IPU, and it just worked. Did not have any problem, apart one problem with GPU compiler, but that's not Enzyme fault. I showed some non-trivial programs using also third-party packages in Julia, which also shows the possibility of reusing code, which is much larger than what can be done in C++. And also thanks to Julia's introspection method programming capabilities, I was able to simplify a little bit how you write IPU programs, although it was still very large, but it's also shorter than what you have to do in a C++. I could use also single precision and half precision, including stochastic rounding, and overall, I think this was a success story for LLVM for being a common framework between vendors and developers. And that's it.
Thank you, Jose. Any questions? Valentin.
Just to make sure, you were live running code on the IPU during your talk?
Yes. When I changed the distribution, for example, I just rerun the code on the IPU.
Impressive. Question from Jesse.
I'm just curious about the stochastic rounding. Can you fix the kernel so that you get reproducibility even with stochastic rounding? Or this is an IPU question.
You mean fix the seed?
Yeah.
I don't remember. Maybe I don't remember.
Okay.
How slow is stochastic rounding?
Yes, that's a great question because I showed it here. Yes. Since this is implemented in hardware, you basically get the same performance using both nearest rounding and stochastic rounding.
Okay.
So I was running the two kernels in parallel using the two modes, stochastic and nearest, but they're exactly the same. Because this is done on hardware.
How slow would it be if it's done not done on hardware?
So we have the package in Julia by Milan, who is not here today, but in terms of performance, it's not great. Instead, this is very, very good because it's free in terms of performance.
More questions? Okay, then let's thank Jose again. Okay, our next talk is on AlgoVivo and energy-based formulation for soft-bodied virtual creatures.
Yeah, thanks. So hi everyone. So I'm going to talk about virtual creatures, and it's actually very nice that we are here at MIT because this concept of virtual creatures has a very long history that dates back to the pioneering work by Carl Sims, who is an MIT graduate. So he introduced this concept in a seminal SIGGRAPH paper in the context of computer animation in the 90s. And actually, in this building, on the first floor, you probably have seen this fluid simulation demo by the elevators. That was created by Carl Sims. That's the same person who pioneered this concept of virtual creatures for computer animation in the 90s. So computer animation is something that I'm also very interested in. It's one of the main motivations behind my personal work. But I would say, more generally, I'm interested in computational models for neuromuscular control. It's just that computer animation happens to be one particular application that I find very useful, very interesting of this particular topic. So concretely, what I mean is, so the basic setup is we have a simulation. So this is a finite element simulation. So this is not that different from what you would find in like mechanical engineering with a finite element simulation. This is using Neo-Hookean elasticity. But I think it gets interesting when we introduce actuation mechanisms. So we also have these controllable fibers. And that's how we can produce animations, like a character animation kind of thing. And this is all driven by a neural network. So there's also like an AI machine learning component. So there's a neural network that is constantly perceiving the state of the agent. And based on that, it produces muscle commands. And that's how we can produce these physics-based animations. And when I say animation, I don't mean like animations just by arbitrarily changing pixels or arbitrarily moving vertex positions. It's still based on physics. It's just that we are basically introducing some actuation mechanism. Now, these muscle control signals, they might look periodic. They are not actually periodic. It's actually a neural network. So this can actually react to user interaction. So if I move this around, you can see how the signals change a little bit. So there's like a sensory motor control loop that is kind of perceiving the state of the agent. And it can eventually recover from those perturbations if you just leave it alone for a little while. Yeah, so this is an open source project. You can find it on this GitHub repo. It was implemented with Enzyme. And I'm going to tell you more about it. So I'm going to tell you more about the specific technical details about this, why Enzyme was particularly useful for this type of implementation. But I also want to say a few things more generally, just, I guess, general principles, general ways in which we can kind of rethink how we implement physics simulations nowadays that we have very advanced simulation very advanced automatic differentiation systems like Enzyme. And also these days that everybody's talking about machine learning, AI, how does that fit into this picture where we want to maybe combine ideas from both fields, physics simulation, machine learning, and so on. And at the core of all of this is really automatic differentiation and gradient-based optimization. So I guess some basics, really one initial way in which we can understand these types of simulation that I'm talking about is by potential energy minimization. And we also saw a little bit of this in previous presentations. So this is a very simple mass spring system where there's an energy minimization loop. So we're trying to minimize the elastic potential. So what you see here is the elastic potential energy. So if I deform the springs, the energy goes up, but then because there's a gradient-based minimization loop, it eventually goes back down to 0. And you can think of this as basically running an optimization loop where we are trying to find optimal vertex positions to minimize the elastic potential energy. This is just for demonstration purposes, how you might do it with a very simple gradient descent loop. In practice, you might do something a bit more sophisticated than this, but you get the idea. And I think especially for people in this room who have already embraced automatic differentiation, I think it's better to think in terms of energy minimization rather than forces or differential equations. I don't know if this is going to sound a little bit controversial, but I really think the important part is the energy, because, and this is in contrast to maybe what you might find in some physics formulations that emphasize the force as the primary definition. The force is just the negative gradient of the potential energy. So I think, especially in the context of automatic differentiation, it's easier to think of the potential energy as the primary definition. And then the force is just something that you can compute automatically with Enzyme or whatever automatic differentiation system you like. And that's the view that I have when I implement this simulation. I know there's something missing here. Some of you are probably thinking, what about F equals ma? What about like integration, inertia? I'll come back to that in a moment. But before that, let me just show you the full engine. So the actual simulation that I'm using is not just a mass spring system. It actually has multiple components, including Hookean elasticity for the triangles. And this is important to maintain shape in 2D. So what you see here is a plot of the potential energy of this edge, this pink edge. So you can see I can still perturb the system and change the potential energy. It eventually goes back to 0. But then the way we can introduce actions, like some muscle-based, some muscle-like actuation mechanism, is also just in terms of potential energy. So we have this action signal that basically reshapes the potential energy. So there's no, like, we're not just like arbitrarily moving vertices. We're not just arbitrarily changing the length of the spring. We're just changing the potential energy, which means that there's going to be a new local minimum that minimizes that potential energy. But the whole thing is still driven by a minimization loop. And so, yeah, so we have these basic components like triangles, vertices, springs that act like muscles. And then you just put a bunch of these things together in interesting ways, and you can get simulations like this. But again, I want to emphasize this, again, this is just a minimization loop. Like everything you see here is just running some minimization loop. It's just that we have multiple energy components. Now, I know some of these components are not really potential energies in the strict traditional sense. And I'm going to explain more a little bit about this in a moment. But when I say energy, sometimes there might be a little bit of ambiguity, because sometimes I use energy to refer informally to whatever it is that we are minimizing to update the simulation. So concretely, what one simulation update looks like is like this. So we have vertex positions and velocities. That's our state that we want to evolve over time. And this is what you do how you evolve the system one step forwards in time. You have basically a minimization loop that is trying to minimize this loss or energy function that includes contributions from the potential energy and from inertia. Sometimes I think of this inertia component as an inertial energy, but again, I know this is not really a thing in physics. It's just kind of like an informal term. It's like a penalty term that penalizes when your vertices deviate too much from purely inertial predictions. So I kind of think of it as an energy informally. Another important thing here is that these energies are not just functions of positions, because in this more generalized notion of energy, they can also depend on velocities. That's how we can also do things like friction, for example, which I know traditionally you would say these are non-conservative forces, so they don't really have a potential energy associated with them, but you can still formulate it with an energy-like term. And that's what I do in these simulations as well. Now, if I didn't know anything about physics and you told me you can implement simulations just by minimizing this thing, that would already be good enough for me. That would be very intuitive. That would be very easy to implement. But maybe this is not going to be enough for people who really like differential equations or integration. So I also have another slide where I want to relate this minimization approach to more traditional formulations of physics, because even though this is what I actually implement, it's not just some arbitrary definition. It actually is what you get when you try to implement certain implicit numerical integration methods that are very stable in practice. So this is how you end up with this type of energy-based or minimization-based formulation. So you start from a differential equation. But then to get closer to an actual solution, you have to transform that differential equation into an integration problem. Now, the integral that you get doesn't really have an analytical solution, so you have to do some kind of numerical integration method with some particular quadrature rule. And there are some simple quadrature rules that lead to explicit numerical integration methods like symplectic Euler, forward Euler, RK4, and so on. But at least for the applications that I'm interested in, usually implicit methods tend to work better. They are more numerically stable, they don't explode, they have just better numerical properties overall. And in those implicit numerical integration methods, you end up with a system of equations that you have to solve. In general, what that means is that we are talking about a nonlinear root finding problem. Now, solving a nonlinear root finding problem in general is very difficult to do reliably. So it turns out that for many implicit numerical integration methods that are useful in practice, you can actually reformulate this nonlinear root finding problem into a gradient-based optimization problem in such a way that any local minimum of this gradient-based optimization problem is a valid solution to the original root finding problem. And that's perfect, right? Because we all know how to reliably find local minima of differentiable functions. And that's what you actually implement. And that's what I showed you before. So because after you do all these formulations, if you look closely at the thing that you're minimizing here, it looks like an energy kind of thing that contains potential energy and inertial energy for some generalized notion of energy. And that's how I think about simulations these days. To me, at least for some reason, this energy minimization-based approach has become like the primary definition in my mind, even though I know you can relate it to some differential equation in the background. And this approach, so the particular integration method that I use for my simulations is backward Euler, but there are many options. And many implicit numerical integration methods can be reformulated as minimization problems. You can find more details in this repo. Maybe, I'm not sure I'm gonna do it justice just with this high-level explanation. There's a lot of details that I'm not mentioning here. Some people might also be thinking this idea of minimization sounds like Lagrangian mechanics, and it's different. It's something else. But I won't really have a lot of time to talk about it, but happy to talk more about it maybe offline. So if this was too much details, maybe let me take a step back and convey the same message again. In this kind of formulation, we don't implement force functions. We implement energy functions, and then we leverage automatic differentiation to compute the force. And the force is just the negative gradient of the potential energy. And this is not just for energy minimization. This can also be extended to proper dynamics with inertia, momentum, and so on. And you know, at the end of the day, all models are wrong. Some are useful. I think this idea of energy minimization is particularly useful, especially now that we have very advanced automatic differentiation systems like Enzyme, and now that we might also want to look into integration with machine learning, where this idea of autodiff and minimization is also at the core of it. So yeah, that's the main thing I wanted to say about just simulation, physics, certain types of physics-based simulation in general. Now I want to say a few things about the locomotion controller optimization part. So yeah, so there are many ways to do it. There are some approaches from reinforcement learning. There's also differentiable simulation. There's also evolutionary algorithms. There are probably many other ways to do it. I won't spend a lot of time speaking about all these different methods, but I figured I would say a few things about differentiable simulation because we're at EnzymeCon, and I assume people are interested in differentiable simulation. But hopefully by now, it's clear to all of you that even if you don't care about differentiable simulation, autodiff still plays a role in the simulation itself, right? Because the force is the negative gradient of the potential energy and so on. So differentiable simulation. So this approach based on energy minimization can be made differentiable. And you can find more details in this paper. But long story short, it's basically differentiable optimization for arbitrary optimizers. And we don't even need to naively enroll through the optimizer. We don't even need to know anything about how you find the local minimum. You can even do non-differentiable operations in your optimizer. It will still work. It's based on an implicit differentiation approach. And there are also some nice autodiff tricks to compute second derivatives and do a linear solve in a matrix-free fashion. And yeah, you can find more details in the paper. But there's a few practical issues with this implementation that I think are fixable, but are still practical problems for me right now. And I'm interested to see if anybody has any potential solutions or suggestions. So sometimes it can get trapped in local minima. It can be difficult to use for long time horizons. It can be tricky to impose hard constraints on the action space. And because of these practical issues, and because I don't really have a very stable implementation that has all the bells and whistles to fix these issues, I actually have I actually use a reinforcement learning approach for my locomotion controllers. I have a more stable implementation of that. So the locomotion demos that I showed you at the beginning, those were optimized with reinforcement learning. Those were not optimized with differentiable simulation. But I think this is an interesting approach. There's just additional work that has to be done to kind of overcome these practical issues. When I was working on this, I used PyTorch. At this time, I didn't know about Enzyme. But I think it would be much better if I used Enzyme. I just haven't done it yet. But if anybody's interested in collaborating or something, I think there's something interesting to do here for differentiable optimization with Enzyme. Because even though the main motivation and the results are for soft body physics, there's really nothing particularly specific to soft body physics. It's really just differentiable optimization. But yeah, anyways. So just for completeness, I also want to say this also works in 3D. It's the same idea. Really nothing fundamentally changes. We can still do the same tricks. It's just that instead of triangles, we have tetrahedra. But we can still do Neo-Hookean elasticity and all the same tricks with muscles and so on. Again, this was implemented with PyTorch because I started working on this before 2020. So I think Enzyme didn't exist before 2020, or at least it wasn't publicly available. But these days, Enzyme is one of my favorite automatic differentiation systems. So this new implementation uses Enzyme. So the energy functions are implemented in C++. I use Enzyme to differentiate them, of course. And then the optimization loop is also implemented in C++. Then I compile the whole thing to WebAssembly, and I can implement a JavaScript library, a JavaScript wrapper. And that's what allows me to show you my simulations here in the browser. And it's not just a video, it's actually interactive. So that's one of the superpowers that we get by just being in the LLVM ecosystem. So we can compile to WebAssembly and all these other targets. I want to say a few more things about this particular web-based environment, WebAssembly environment. So in WebAssembly, there's no garbage collection. You just get an array of bytes, and you can do whatever you want with it. And I also wanted to keep the number of dependencies to a minimum, so I also made the decision not to use libc, and I don't know if I'm going to regret this decision, but so that means I don't have malloc, I don't have free, but I ended up implementing my own malloc and free in JavaScript, and again, I don't know if I'm going to regret the decision at some point, but it's not a big deal for now because I just do my memory allocations at the beginning of the simulation, and then when I run the simulation, it's just pure computation, so there's no additional allocations necessary. But actually, this required a little bit of trial and error because sometimes the optimization passes can introduce memory allocations, even if I don't really have any memory allocations in my implementation. So this can happen. I've seen it happen, I think, in regular LLVM optimizations and also in Enzyme when it computes the backward pass. So if anybody has suggestions to avoid these allocations, that would be very useful. But yeah, that's something about memory allocation in this particular web-based environment where your mallocs are going to happen in JavaScript. So we want to avoid them as much as possible during the simulation. Another nice thing about Enzyme, of course, is we can compile to native code. So I also have another version. It's basically the same C++ source code, but I just compile it to native code, and I have wrappers in Python, so I can do interoperability with PyTorch for neural network training. And that's how I actually train these locomotion controllers. And it's CPU only for now. I haven't really looked into GPU yet, but I know Enzyme supports GPU as well, so that might be interesting to explore at some point. Yeah, so just, I guess, a few words. So let me just re-emphasize the main point, I guess, that goes beyond this particular project, which I think might be useful for people thinking about implementing simulations with autodiff and how this relates to machine learning and other things. So automatic differentiation has an important role to play in simulation, even before we talk about differentiable simulation, because we can just implement the energy function, and then you compute the force automatically by running autodiff. And this can also be extended to implicit numerical integration methods, and we can even make those implicit numerical integration methods differentiable. And I guess more generally, what even is a physics engine? Right now we have, I think, in many contexts, we have a very monolithic view of what is a physics engine, right? Like we have a physics engine for this particular phenomenon, for this particular phenomenon. I think ideally we would have something maybe like, this is a little bit speculative, but I think I would like to see something like what people have in neural networks, where we just have a bunch of differentiable modules, and you just compose them together, and they kind of talk to each other through some minimization of a loss function. I'm doing something similar here for this energy-based approach, where we have like the Newhookian triangle, we have the springs and friction and all these energy terms that are getting minimized. So it's just a collection of energy functions that happen to be minimized in a particular way with some gradient-based optimization method. And at the core of it is really automatic differentiation. So this might be an interesting way to look at simulation. I think especially when you start to think about how this relates to, how you can integrate this with machine learning. I also know that in machine learning, there's this idea of energy-based modeling, which I think is also very related to this idea of energy minimization in physics. So there might be some interesting connections there to kind of bridge that gap. But yeah, that's all I wanted to say. The project is open source. You can find it in this repo. There's also a link to a live demo you can try on your browser, on your phone if you want. Yeah, that's it. Thanks.
Any questions?
I have some very brief follow-ups that we should also have a longer follow-up during the hack session on the memory allocation sort of stuff. So to partially answer the question, when you have data in your forward pass that you need for the reverse pass, first Enzyme will try to prove that you don't need it, in which point it doesn't need to do anything. Then it'll try to prove, is this not overwritten, e.g. is there no aliasing right to it? And then finally, if it decides it needs it and it cannot get it from anywhere else, it will go ahead and try to cache it. Right now, we actually have an internal utility function, just create allocation, that will call one's favorite function. By default, this will be malloc. In Julia, it'll actually be the garbage collected allocation. So we should be able to swap this out to say, if you have a special JavaScript or whatever else named function that you like, that we can go for it. The other recommendation that we should, however, make the syntax like from the syntactic sugar as opposed to the internals thing, a little bit easier to use that. There's one other thing that I might also recommend. There's an sort of like analysis warning. I'm going to probably get the exact name of the error message, but like it's -r pass equals enzyme, and it'll tell you, hi, I needed to cache this variable because of whatever things, and it'll tell you therefore which ones it needs, and possibly you can optimize the code such that it doesn't need allocation of free, even in the reverse pass.
Okay.
Other questions?
And how's the performance of calculating force via AD compared to kind of explicitly encoding the force function from the springs?
Yeah, I don't have that comparison right now, but I didn't show it here, but I also worked on another project where we were doing everything by hand, and that was the main reason was to get performance. So yes, I mean, you can always get more performance if you really invest the time doing it by hand, but I think there's a point where you kind of get diminishing returns. I don't really have any concrete numbers. I'm sure you can get more performance if you compute the forces by hand. I guess what I would like to see is maybe what this new approach can enable, especially where you have problems where you don't even know the force function, maybe you want to do some machine learning on it or something. Maybe that's where this approach could be more useful, but just for performance reasons, I'm not sure that would be the better justification for using this approach.
I'm just curious, do you have a sense of scale of like how many verts you could push this to and still have a wonderful animal like this galloping successfully and your optimization converge, things like that?
Yeah. I haven't tried to push it that far, to be honest, because it's also running in the browser, so it's not really, I'm not really expecting it to be particularly performant, so I just, I haven't tried. But yeah, I would also say I've tried similar approaches in other projects where we expanded this to like 250,000 elements, but it was all done by hand, like the forces, even Hessians and Hessian approximations. Yeah, but for this particular project specifically, very low resolution meshes. I'm not even trying to scale it too much because it's going to run in the browser anyway, but yeah.
And are you using first order methods for this?
So far, yes. I think that, yeah, ideally, I would like to use some kind of quasi-Newton method. I've experimented with that before, but it gets complicated, and to be honest, I originally thought I would eventually have to do it, but it's running in real time, even with a basic gradient descent optimizer, so there's been no need to do it, but maybe at some point it will be necessary.
Okay. Yeah, this is so cool. Thank you so much.
Other questions, comments? Somebody wants to repeat this live? Okay, thanks.
Is it this USB-C? Okay. So hi everyone, my name is Sarah. I am a fourth year PhD student at the University of Texas at Austin. And I'm gonna show, I'm coming at this from like a very application side, but I'm gonna show how I use Enzyme, and specifically how I use it for a differentiable ocean model. This is work that I've done with a bunch of other fabulous collaborators, and they're all listed here, and I'd like to say thank you for all of their help getting my code to this point, especially Billy and Valentine for continually debugging Enzyme. Okay, so like everyone else here, I use Enzyme for derivative computations, and I specifically use Enzyme for derivative computations during something called adjoint methods. A couple other people have mentioned this thus far. These derivatives can then be used for things like parameter sensitivity calculations, data assimilation, or parameter estimation problems, and those are kind of like the general work that we do with ocean models. And then, yeah, so like we apply these adjoint methods to ocean models. I've highlighted two of the three here, data assimilation and parameter estimation, because these are the two that I specifically focus on. So I use high resolution data to try to improve parameters in ocean models. So that being said, my talk is going to kind of cover the methods that I use. So this is going to go over what the adjoint method is. Depending on your background, this might just be like general review. And then I'll cover the ocean model that I work with and show an explicit example using Enzyme to compute a derivative. And then I'm going to talk a little bit about eddy parameterizations, which is my focal point of my dissertation. This won't go into too much detail, but I hope it'll give a general summary. Okay, so getting started. So like everyone else, I compute derivatives of a loss function j, and that's what the adjoint method aims to do. So a loss function is just like a scalar valued output that has something to do with my model. This can be a diagnostic quantity. It could just be an entry in a state. The adjoint method specifically computes derivatives of this loss via Lagrangian method. So we define this Lagrangian L. It's a difference of my loss function and a sum over the states in my integration of, let's see, so we have mu of t, which is my Lagrange multiplier. You also hear me call this the adjoint variable. We have the state variable x of t, and then we have L of x of t, which is my model time step. So this takes the state x of t to x of t plus delta t. And what we're going to do to find the derivatives that we want is we're going to minimize our Lagrangian. So going back to calculus 1, the way that we do this is we take derivatives and we set them equal to 0. So I wanted to kind of show specifically where Enzyme comes into play. So like I said, we're going to take derivatives of our Lagrangian. So doing so reveals something that we refer to as the normal equations. The first set of normal equation is the derivative of my Lagrangian with respect to my adjoint variables. If I set this equal to 0, what this does is it returns my my equations of motion. So if I move this L over, I literally just have my model integrator, which is great. The second normal equation I have here is the derivative of L with respect to the state at the final time step. This defines for me an initial adjoint value. So this is kind of, I say initial in quotes because it exists at the final time step. And then the last set of normal equations gives me a relationship between mu of t and mu of t plus 1. So this is how we actually backpropagate these adjoint variables during the adjoint method. So you can kind of think of this as a forward method. So like we have a forward run, which is our integration, and then we have the backwards run, which is computing all of these adjoint variables. And you don't need to memorize any of these equations. Like this is just kind of a general framework of how we actually compute these derivatives. I wanted to highlight one term in the final normal equations. This is the derivative of L with respect to the state acting on the prior adjoint variable, and this is actually where I think of Enzyme. So I think of Enzyme as taking a full model derivative. And given that I work with ocean models, this is actually really impressive because I usually have some complicated set of equations. Enzyme can take the derivative of this with respect to my state. And it keeps track of the backpropagation for me, so I don't have to do any hard lifting. So seeing equations is nice, but I wanted to give a couple little adjoint walkthroughs of ways that we can use these derivatives or what ends up happening. So like, let's say I wanted to understand how sensitive my final state is to my initial condition. So like, this is just like what happens if I shift my initial condition. My loss function would end up being the final state, or if my final state is multidimensional, this would just be like an entry in the final state. I want to compute the derivative of this loss with respect to my initial condition, and through the adjoint equations, this actually ends up just being my final adjoint variable, or the initial adjoint variable, however you want to look at it. So this kind of gives you physical meaning to these variables, and so Enzyme would run the forward and then the backwards, and we end up getting this derivative. So another way that we can use adjoint methods is, let's say I have some uncertain model parameter, but I have high resolution data that could theoretically inform me how I can better improve this parameter. In this case, your loss function would be something like a model data misfit, and our goal is to compute the derivative of this with respect to the parameter alpha. And again, with the adjoint equations, what this ends up being is actually a sum over all of my adjoint variables. So it just ends up, being the sum specifically of mu times the derivative of L with respect to my parameter. And Enzyme, again, can do this for me. So I don't need to keep track of this sum. I don't need to do any work. Enzyme can find this derivative on its own. And then in order to improve the parameter, we would need to optimize. So we take this derivative when we step towards a hopefully improved alpha. So I like these examples because they give me meaning to what these mu's are. And so like Joe mentioned, there is one hiccup to the adjoint method. Specifically, when L is a nonlinear model, taking the derivative of this with respect to the state requires me to know what x of t is. This is independent of the adjoint method choices you've made. It's also not possible for most ocean models or Earth system models. I can't store the state at every time step. I would very quickly run out of memory, and it wouldn't be possible to actually compute derivatives like this. And so luckily, there's a method/package in Julia that can help me. And this is checkpointing.jl. And so I make heavy use of checkpointing in order to run my adjoint methods. This is being developed by Michelle back there along with someone else at Argonne named Krishna. It checkpoints the adjoint method for me, but it does come at a trade-off. We'll use less memory, but we will have much longer computation time. And so showing what that means, like let's say I have some initial condition. I'm going to store my initial condition in memory, and then I'm going to integrate my model forward, and all of these orange arrowed states, I store these states. So these are actually getting stored in memory. And then when I get to my final state, I know how to compute my initial adjoint variable. So I can go back to this prior checkpoint and actually reintegrate the states between this and the final state. And then using those reintegrated states, I can actually backpropagate mu of big T back to mu of T6 and continue on doing this. But what this ends up meaning is that I need to reintegrate my whole forward problem once in order to actually bring mu of T6 or mu of big T backwards to T0. And then there's also instances where you can't even store all of the states in between two checkpoints in memory, so you would need to do double layer checkpointing. And every layer you add adds a whole other integration. But it does make it possible to use adjoint methods for large ocean models. Okay, so finishing up with the methods, I just wanted to cover a little bit of why we're so interested in adjoints and automatic differentiation in my group. So finite different methods produce a gradient, but this gradient is not necessarily as accurate. Adjoint methods are theoretically an exact gradient. I say theoretically because there will always be machine round-off error. There's always going to be systems you can't technically apply adjoint methods to. but most of the time they produce a really good gradient, and this can help with your optimization scheme. Another place that adjoints really shine is if we have a high-dimensional control space. This is to say I have some loss function. I want to take a derivative of my loss function with respect to something that's high-dimensional. Like this can just be your initial condition, and even for a coarse model, your initial condition might be 100 by 100. And if I wanted to do this with finite differences, I would need to do 100 squared finite difference problems, and I'd rather not do that, but adjoint methods can find this derivative for me all at once. Automatic differentiation is really nice for this because L might be a really complicated model. I don't really want to write my derivative code by hand, and this is not to say that you can't do it. There are actually people who write their derivative code by hand. I just prefer not to, and I let Enzyme generate derivative code. And also, automatic differentiation is nice because my model code might change over time. So if I want to change something in my forward integration, then if I had written my derivative code by hand, I would theoretically need to think about all of the ways that this change in my code will change my derivative code. And Enzyme is technically indifferent to model changes, so I don't need to worry about this. Okay, so that is all of what I do with Enzyme and derivatives, and now I wanted to show the ocean model that I've differentiated in Julia and give an example using it to compute a sensitivity field. So I work with a shallow water model. This is to say that I have, you can think of it as like a box of fluid. I have some wind blowing on the box, it generates circulation. I have 3 state variables in my system. I have u, v, and eta. So u and v are the components of my velocity vector. Eta is the surface displacement, so as I circulate the fluid, my fluid kind of waves. Eta is that displacement. It's discretized on an Arakawa C grid. This is just to say tracer values live in cell centers. The velocities live on the cell faces. And all of the model code is in this package by Milankovo, shallowwaters.jl. It's really nice. It's super customizable. And I've basically fiddled with it to make it differentiable and to do the experiments that I'd like to with it. And this is just a snapshot of the high resolution velocity. So let's pretend that I wanted to understand, so like this is some measure of kinetic energy at the final time step, and let's pretend I want to understand how sensitive this energy is to, say, my initial x velocity, because x actually goes into computing this energy. What I did is I spun my model up for 10 years, and then I used the 10-year spin-up state as my initial condition, and I do a 1-year forward problem and then a 1-year backwards problem after the 10 years to compute the sensitivity. We'll use reverse mode enzyme and checkpointing to compute this above derivative with checkpoints. And so what we end up getting is this. This is what we would call like a sensitivity field. So every point on this figure is a gradient. The red values are positive, blue values are negative. And what this tells me is precisely like if I were to change my initial condition somewhere right here in this negative area, then I would expect that my final energy would decrease by a little bit. And similarly, if I wanted to change the value here, then I'd expect my final energy to increase. This is like a very simple example of using adjoint methods for derivative or sensitivity analysis. People do really cool stuff with this with ocean models. You can actually look at things like how sensitive circulation is in the Atlantic to things like wind stress, for example. Okay, so now I'm going to finish up by just talking about eddy parameterization. So this is my specific application and where I hope to go with all of this work. So first thing, what is an eddy parameterization? So when we run global circulation models or ocean models, we are limited by computational cost. We can't just make our model as fine as we would hope to, so there's always going to be some loss of information. And so specifically, we lose this information that exists below our resolved scale. This is why it's called subgrid scale processes. You might have heard this term. I think Patrick mentioned it. They're basically just physics that exists below your resolved scale that you don't resolve in your ocean model. And so the way that we work around this to keep our predictions of, say, ocean circulation accurate is we implement something called a parameterization. And so what I have here are the equations for that shallow water model. So these are just the equations of motion. You can ignore most of it, but on the time derivatives of the x and y velocities, there's this term on the right-hand side, s sub x and s sub y. This is a parameterization. So we essentially think of it as an extra forcing term, or specifically that's how I view it. And we just add it to the right-hand side of our equations. And the idea is that we would add something that would capture, say, statistical information on the missing physics. And then I wanted to cover why eddy parameterizations are important for ocean models. So when we run our ocean model, we have some atmospheric forcing. This injects potential energy into our system, and eddies provide a key pathway between potential energy and kinetic energy. So if you don't resolve eddies at all, you just don't get this conversion of potential to kinetic energy, and you will always have too little kinetic energy in your system. And another thing that eddies do is they drive something called this inverse energy cascade, or inverse backscatter. And so they take energy, or they specifically drive kinetic energy from small scales back up to large scale. So eddies exist at something like 10 to 100 kilometers. Large scale would be anything over 100 kilometers in our ocean. And without having this inverse cascade, we're losing information about the overall circulation and thus leading to a less accurate general circulation model. And so it's really important to capture A, the conversion of potential to kinetic energy, and then B, this inverse cascade. Okay. So this is what happens with the Milan's model when I added a parameterization. So specifically, the blue line here is my low resolution spin up. So this is a measure of kinetic energy in the system. This is the spin up over 10 years. Blue is before any parameterization has been added, and you can see that when we look at it and compare it to this like yellowish line, this is my high resolution or eddy resolving model. There's very clearly a large discrepancy in the kinetic energy in the system. We just have less of it. But when we add the parameterization, which are, one of them is the purple and one of them is the green, you can see that I've injected kinetic energy into the system. This doesn't necessarily mean that I am A, doing the right thing, or B, that I've captured the inverse backscatter. There's a lot of other diagnostics to check. But at the very least, I know that my parameterization has added energy into the system. And so our goal would be to further improve the green and the purple line in the parameterization scheme. Okay, so yeah, so this is what I just said. So our goal will be to use adjoint methods to potentially tune our eddy parameterization. So if I think of my eddy parameterization as a function of my velocities, and there's some coefficient gamma, I can theoretically use adjoint methods to compute a derivative of a model data misfit, say, with respect to gamma, and try to use some optimization scheme to improve what gamma is. And so I've started to do this. This is not a super exciting example, but what I've done is past the 10-year spin up. This is a 90-day integration. The blue line at the bottom is, again, no parameterization. The purple is my high resolution. Orange is where I've implemented a parameterization, and green is where I've begun to try to optimize for gamma. So I've used enzyme and checkpointing to compute a derivative, and then I used optim.jl to run an optimization scheme to try to improve the prediction of the parameterization from the orange line. And this was like just a very early example. This doesn't mean that I have successfully captured backscatter, but it does show that the adjoint method can adjust your parameterization and specifically adjust where the energy lies. Yeah, and so that's all I really have. Patrick mentioned, I mostly wanted to highlight one thing about using adjoint methods, because Patrick mentioned this yesterday, and I feel like I should say something, which is that the adjoint method is really promising because it lies in this new realm of online learning. Specifically, you might have heard this in the context of machine learning, but the idea is that we can actually use diagnostic information from our model to tune these parameterizations, which hasn't actually really been done before. So we can use things like energy, we can use energy spectra, we can use a kinetic energy transfer to tune the parameterizations, and these would theoretically do a much better job at capturing eddy statistics than just using like a model residual, which is what's been done in the past. And so the adjoint method is very promising, but yeah, I can go more into this if anyone's interested, but that's the general idea, is that we can use new information to tune eddy parameterizations. And like Patrick said, Google has done this really successfully recently with an atmospheric model. And then there was another paper that did this really successfully with a quasi-geostrophic turbulence model. But yeah, so that's about what I have. So thank you. Yeah.
Question? We actually have a question from the YouTube live chat, which is, when there are linear solvers in the forward equations, do you solve the adjoint equation, or does enzyme do that?
Ooh, so it is linear solvers is in AX equals B. So Milan's model is fully explicit. I don't need to worry about doing any nonlinear solves. Otherwise, I wouldn't be able to use enzyme through the nonlinear solves. And the way that we would work around this is actually using enzyme for everything but the nonlinear solve, and then you would handwrite the adjoint part of the nonlinear method to add that manually to your adjoint variables. But I don't need to worry about that with shallowwaters.jl.
Other questions? Yes.
Did you do this on CPU or GPU?
CPU. Yeah.
Have you tried it all on GPU?
I don't know how. I don't think that enzyme really runs on GPUs right now, but I could be mistaken.
You can do.
Shadowwaters.jl doesn't support GPUs yet.
Ah. Yeah. Yes.
Follow-up question, is that parallelized or zero?
Ooh, it's not. So this is still a very much baby ocean model. Like, it is just a single layer model. I don't have any changes in the z direction. There's no need to parallelize this.
Okay. Other questions, comments? If not, let's thank Sarah again. And our last and greatest talk. That's why it's the last. Do you want mirroring?
Yeah, sure. That would.
Choose to do that. Yep. Here we go.
Thank you. Hi. So I will be presenting something that we are trying from past 1 year. That is a descriptor library that uses automatic differentiation instead of like analytical derivatives, and how well it integrates within our system. And I will also like to give like a very, very brief intro of what exactly is this used in, that what exactly is the KIM initiative that I am part of. So KIM stands for Knowledge Base of Interatomic Potentials. We are, as a group, we are mostly based in University of Minnesota, but it's not limited to University of Minnesota. We have collaborators in your University of Florida. Now our software is being used as a core of one of the project of Lawrence Livermore, where they are basically using it as a simple evaluation system on top of which they will build their own core logic. And we also have deep ties with New York University, which is graciously giving us a lot of hardware to host all of our stuff, as well as now it's also being evaluated inside Intel and AWS for their own material and machine learning research. So what exactly is OpenKIM? So like I said, it's like an repository of potentials plus some peripheral tools that you need for all of those things. And the core goal of this project is can be summarized like in 3 words. It wants to make all the meta simulations reliable, reproducible, and accessible. And all the codes and everything is hosted on openkim.org if anybody wants to check. Once it started, they realized that for making whole thing reproducible, you don't only need the executing code, don't only need the models, you also need the data sets on which everything was trained on, because 2 different data sets can give 2 wildly different parameters. So a sister project started that is called CollabFit, which is basically about archiving all the data sets that we need for training any model. And what it does is it specifies your protocol that how a data should be formatted for your materials research, and it tries to get any data that it can and formats it in that particular format, and then saves that particular data for online reuse. So after first year of its inception, what it has done is it has like, I think over 100 million configurations. I think it has like 150 or so data sets that it archived, it changed, it's basically cleaned them up, made sure everything is consistently formatted, that when you call something like give me energy of this configuration, give me energy of this particular atomic environment, it means the same thing across different data sets like that. And after cleaning it all up, it has put it one place. So we had the models, we had the data set that was there. So the next logical step was, why not build a large model on top of it? And so we got into the third project that is called FERMA. Basically, it's foundational embedded representation for materials or for matter. And the goal of FERMA is that, okay, let's take all of these models and let's take all of these data and come up with something that is greater than all of that. And we were actually quite, the proposal that we submitted for FERMA was actually just in nick of time, because 2 days before the deadline of that submission was, ChatGPT was launched. And we were like pretty large about, oh, we will make a large language model or we will make a model that is akin to what GPT 3.5 is doing for languages. And then suddenly ChatGPT launched and we submitted the application and it got funded. So it was like pretty nice timing on our end. And one important piece of software is called KIM API, which is basically an API standard that we defined, using which you can have any arbitrary simulator that you want to use, any arbitrary code that you want to use. And it will basically act like a layer where you can get energy and forces. You can give it the atomic configurations, that is the position of atoms, etc., and it will get you back what should be the force and energy of this particular configuration. And as an example implementation of this API, we do provide it implementation in 3 languages, that is C, C++, and Fortran. But it's basically anyone can implement this particular API, and you can access all of these potentials directly. Who are like core PIs? Like I said, it was started in 2009 in University of Minnesota. Professor Ella Tadmore is the PI of this project. The Kim API was mostly designed by Professor Ryan Elliott. And now we have all the machine learning work is mostly done by Professor Ella Tadmore and Stefano Martignani from NYU. Okay, so what exactly is Kim API? How exactly does it function? On a pretty reductionist level, I must say, this is basically how it works, that you have any software of your choice, which is called the simulator, such as your LAMPS, which stands for Large Atomic Massively Parallel Simulator or something, or GROMACS or anything that you like. It will give a configuration, that is positions of atoms and your coordinates, to the Kim API, and Kim API will basically have two different working components. One is called model and one is called driver. The driver is the actual C++ code where your functions are implemented, which will do all the calculations. Your model is basically just a list, a human-readable text file that contains all the parameters that particular C++ code needs. So your model driver is like a class, and your portable model is like an instantiation of that class for particular material. And this will execute and return back energy and forces to the simulator, so that whole simulation can progress. Okay, so coming on those 3 points about reproducibility and your reliability, etc. So what this model gives us is that we have to just implement the core logic or the core function just once, the C++ code, and now we can just take different instantiation of that particular model, different set of parameters, and we know all of them will work exactly the same. So they are actually really reproducible. But our reliability, this pretty small, like tiny list of things, is that we implemented lots of different tests for each particular physical property of a material. And every time a new model gets submitted, we evaluate them on all of these properties to see how well it behaves. So that what happens in most of machine learning models is that people usually evaluate them only against energy and forces, that, oh, see, our model gives forces with this accuracy, energy with this accuracy, but when we actually use it in some simulation, it just completely fails. So in this case, what we do is we measure its property, like, oh, how well can you calculate the structure of this particular material, how off it is from the actual property, how well can you do this melt simulation, and how off your melting point is from this particular reference value, etc. And we can do that for all known crystal structures. This is currently being pushed in where given two materials, suppose if you say, oh, my model works with aluminum and iron, it will basically try to find all the crystals that can have aluminum and iron in all possible stoichiometry and symmetries, and it will run all of these tests to give you like a brief idea. And what about accessibility? So if suppose there is a model that you like, it's really easy to install. Just if Kim API is on your system, you can just give install and give the model name. It will figure out what dependencies you need, what is the C++ code that you need, and it will compile and install everything on your system. And you can work with it out of the box if you use LAMPS, ASE, DL, Poly, and GULP. If you use some other simulator, it's really not that difficult to extend. And to make sure that it is accessible to most users, it is installable via Conda, APT, your DNF, Brew, or almost any binary package distributor that is out there, as well as from source. Although the person who was maintaining all of these, he just finally gave up, like the Linux binary distribution, I can't handle with it. So now we are just going back to Conda and Spec. So if you want from source, you can use Spec, otherwise just use Conda and it works easily. So why all of this? Till now, your Kim API was only dealing with your so-called physics-based models, where your models are basically based on some physical principle that, oh, let's assume electrons have a uniform density, and then we are trying to do this. So their functional form is really, really fixed. There's nothing much you can do about it. What you need is just to change the parameters for each particular model. And it worked really well for all of that kind of work. But then machine learning models exploded on the scene, and now everybody wants to use machine learning models because they are way more costly than your good old physics-based models, but they are way more accurate than those particular models. And the problem with machine learning models is that they can't fit in this kind of format. The driver for the machine learning model, the functional form, is not fixed. And every user or even every iteration might have a different functional form. So there's no way we can actually give like a a constant C++ implementation of a neural network and assume everyone use exactly the same neural network. So idea was that, okay, we need to implement something else to make all of these things work. How exactly it is in the community right now, they are basically silos of each research group. Everyone comes up with their own Python package, their own C++ code that they implement to run the simulations, etc. So this snapshot is from the simulator called LAMPS, which is one of the most popularly one that is used. And you can see each machine learning group has their own package in the distribution. And if you want to use one, you have no idea how to translate it to other. And every time you have to go through the documentation again and again. And there is no chance of getting a proper verification or validation if you have these kind of approach. So we said, OK, let's have a kind of a standard that can cover all of these cases. But we did not want to run into this that XKCD scenario. So one thing was clear: we can't implement a new standard. We have to do with what exactly what is existing. And luckily, Kim API is already a part of core LAMPS distribution, so we don't need to add anything new to it. We already had the potential distribution, et cetera. All we needed was to connect the dots with our own trainer framework, and it will work out of the box with this one. OK, so this was the logic that was presented. That what we will do is, if you have, let's tackle PyTorch first, because they have really good C++ API, whereas in TensorFlow, et cetera, it was way more difficult. So the idea was that when you will get configuration from simulator, it will decide what kind of model do you want to run. Broadly, you can divide the machine learning models into two parts: one that uses descriptors and one that uses graphs. I'll come to the descriptor part later. Graph is just basically like a list of which atom is connected to which atom, and you just use that to calculate something called message passing and calculate the energy and forces. And for all of these, it uses the libtorch or the PyTorch C++ API directly, and it can compute using that, the gradient, and it works. Problem comes if you have descriptors, because if you are using descriptor-based models, then when you ask PyTorch to give you the derivatives, it gives you the derivative against the descriptor and not against the positions. For forces, we want descriptor against the position vectors. So there is an additional step where we want the Jacobians of your descriptor with respect to the positions, and we have to compute the vector Jacobian products to get the forces. This is where Enzyme actually came into picture. So we wanted to make sure that all of this is portable, so that even if someone runs it on any particular platform, they should have the access to the descriptors as well. So the first idea was, OK, let's implement descriptors in functions that calculate descriptors in your something like PyTorch. But first, like, what exactly were descriptors, or what are descriptors? So descriptors are basically like an invariant mapping that takes in a 3D structure, the positions and the species of atoms, et cetera, and they map it to a feature space, which is like a vector of fixed length. It solves several problems. Like, first of all, it gives you a representation of constant width. So you can actually use it in some other model. Irrespective of how many atoms are there or in what orientation they are, you should always get the same dimension of the feature space. Because it's molecules, they should also follow certain symmetries. Like if you rotate a methane molecule, it is still a methane molecule, and its energy and forces should still remain the same. So things such as rotations or your translations or permutation, if you replace one hydrogen with the other one, it should not change the representation of it. So it has to obey these kind of symmetries. And one additional benefit is something, or one additional requirement is something called smoothness, that if I take one particular structure and I perturb it slightly, the same should be reflected in its feature space. It should not be like now it's completely different space. And there is a lot of research has already been done in these descriptors, and this tree came from this particular paper at the bottom, and they kind of try to organize every different descriptors, how we define it. There are two major ways that we focused on it. One is your atomic symmetry functions on the top, which is basically you take all the angles and all the distances that are there in your system, and you map them to some set of functions so that you get like an output width that is fixed. And the second, a more robust and more popular approach is called your density correlation features, where you assume that each atom is basically like a 3D Dirac delta function. And then you can project those Dirac delta function into some sort of like a tensor representation and do some mathematics with it to make them invariant. The difference is like whether you want those Dirac delta functions to be like a point, basically like an ideal Dirac delta function, which makes it somewhat more difficult to carry out mathematical operations, or you can assume that each of them is like a very sharp Gaussian, and then a lot of your things becomes easy. Why do all of this? Because what these descriptors do is they shift the complexity of learning a potential from your machine learning model to the representation part. If you use something such as graph neural networks, your representation is simple, that you have to just give it the coordinates and it will give you energy and forces, but then your model becomes really expensive and really complicated. In this case, two of the most used models are called SNAP and GAP. One of them is linear, one of them is just your Gaussian kernel-based method. And so they take in the descriptor and they apply really simple mathematics to it, and they get reasonable accuracy. The benefit of these kind of your models is that although their accuracy is somewhat limited, they are really high performance. So you can scale them across like 1 million atoms and they will work. Whereas if you take modern machine learning methods such as your graph neural networks, they don't scale that well. And second, their failures have like bounds. So what that means is that one of the biggest complaints that people say about machine learning models is when they work, they work. When they fail, it's basically like not even wrong. You will get an energy of methane molecule that is like more than the entire atomic bomb explosion kind of things. But in this case, it's more limited. You can predict when it fails, what should be the maximum energy, et cetera, that it will give. So you can do some sort of analysis on that one. What are the existing solutions? So there are libraries that compute exactly that. Describe is one of the most popular one. libatoms is used by GAP that I just showed, and it is one of the most used one. They are really high performant. They are easy to use. They're pretty well designed and coherent libraries. One of their best features is they have analytical gradients, and I also count it as like somewhat of a negative because of reasons that will come later. The biggest problem that we faced with these was they were difficult to extend. Like how would you actually use it in a C++ code? It was not clear. Although all of these libraries are C++ at the back end, it is still not easy to extend them or link against them. They are even difficult to work with other ML frameworks. So as long as you are using their own framework, it works very well. It is really integrated. But suppose you want to do your own model where you want input from these things, then it becomes pretty difficult how you will actually flow your gradients through them and all that. Third is limited differentiability. Most of these one have like few parameters that you want to optimize, and only way to optimize them is something such as your grid-based search, et cetera, or some sort of Bayesian search, because there is no way you can take derivatives against those parameters. If you want to do that, you have to do it by pen and paper and then implement it yourself. And finally, the most important part was transferability. That fine, I can train it in Python, but I want to use it in some simulator that is running on C++. How exactly I will take exact settings there. So we said, okay, let's implement the whole thing in PyTorch and get it over with. It will come, because of Torch script, everything will be portable. So we implemented a simple Stillinger-Weber model in different automatic differentiation frameworks, and we tried to calculate its energy and forces. Why? Because most of your your frameworks such as PyTorch and your TensorFlow, they are really efficient in doing linear algebra or those kind of operations. But most of the scientific code is like highly mutating. It has a lot of ifs and like for loops, etc. And that's why they are not that ideal for those kind of work. So we wanted to see how much of a penalty that we will get. And it was like, no surprise, it was really, really bad. And if we use that in simulation, this will be the biggest bottleneck that we will face. Other solutions such as Julia with Zygote, because I don't think Enzyme was there at that time. So Julia with Zygote performed really well, but again, it's Julia, and it was really difficult to integrate anywhere in our own workflow. So finally, we said, okay, let's try a different C++ one. One of the option was AutoDiff, which is a header file only automatic differentiation framework. It was really easy to install, but the performance was, I guess, fine, and we might have gone that way. But then we looked at the numbers that we got from Enzyme, and like when we first got it was like, okay, there is something wrong, because when we were using our own analytical functions, Enzyme generated gradients were giving lesser value than our own analytical function, that is the Kim part of this graph. So it was like, okay, either we have implemented it really bad or there is something wrong going on. So we took out the core logic of gradient calculation, etc., and we implemented it in a single standalone C++ file so that we can have like an apples-to-apples comparison. And I guess to our disappointment, turned out analytical function was still faster, but they were only now 6 times slower than Enzyme. The benefit of this is, however, that now, because gradients computed by Enzyme was so fast, that the vast majority of time is not gradient calculation. It is actually the bookkeeping, like calculating neighbor lists, which atom is where, etc., and all of transfer of control, like from Python to C++ and those kind of things. So that means if we use Enzyme in your enzyme-generated gradients in our simulations, we will not see 6 times slow up. We will only see like at most like twice the slow down. So it is now a really viable solution. It gives in the same ballpark as your analytical gradients. So that settled the question that, okay, it is most likely the best way forward that we can use Enzyme to actually generate the gradients. So came the first design preview of our library, which was called DibDescriptor. And the idea we had was, okay, there already exist these great libraries such as your Describe, etc., and all of them have C++ background, or maybe Fortran. And Enzyme claims that it can differentiate through everything. So what we can do is we can make some sort of like a Frankenstein library. We can gobble up the codes from all of these, compile, put them in like a single your wrapper, and then just use Enzyme to compile through all of them, and we will have a descriptor library. And we can then link Py 11 code to it so that we can transfer it across Python and C++. We can train in PyTorch, and those settings we can save and then run those settings in C++, and it will be great. However, that did not, our excitement was short-lived, because differentiating some arbitrary code that you got online, your mileage will vary a lot. Most of them had their own really complicated internal memory allocation structures, etc., their own way of denoting data. So within like first month, we gave up that this is not a way to do. Only thing is we can actually start from scratch and just write our own and get it over with. So the basic design preview was, or basic design that we came up with was that we will have like a broad namespace which will have functions like computing the descriptors, for computing the gradients, and computing Jacobians, etc. And we will have like a parent class called descriptor kind, which will have some pure virtual function called compute. And all you need to do is just extend that particular function, and your compute function will take care of it, and you will get the gradients automatically. We have implemented 4 of them. There were certain like hiccups along the way. For example, you will see that there is one function called cloneMT, which is present in every child class. Technically, this function should be a pure virtual function in the parent class, but for some reason, Enzyme your seg faults if I give 2 virtual functions. With single virtual function, it works fine. So I decided compute should be the virtual function, pure virtual function, whereas your cloneMT can be like a function that will each class implement separately. CloneMT was actually needed for that virtual reverse that we need to provide with Enzyme if we want to differentiate against the whole class. Okay, so what this gave us was the uniform API that we actually wanted. Suppose if you have your descriptor is defined in a certain fashion in a text file called descriptor.dat, you can use that same file in C++ and Python, and you will get exactly the same derivatives in both cases, and your workflow will remain largely the same. Yeah, I'm sorry about these, your switching from camel case and your snake case, your underscore, because this is what happens when a single person is writing the library, because I can switch to whatever I want and there's no one stopping me. So it's always like whichever is fastest under my fingers. I have to fix the notation properly, but someday, I guess. Okay, and like I said, extending these is really easy. Just inherit the descriptor kind class and implement the compute function that will calculate your descriptor for a single atom of a given index, and you are done. You will automatically get derivatives. Right now, you have to also add a switch statement in compute method where you can say, oh, for this descriptor kind, do this. That is because ideally, this compute function can use a templated method, and it should work out of the box. But I have always had like hard time with Enzyme and templates, so I tend to avoid them unless they are really needed. Okay, And the biggest added benefit, we can not only differentiate against your positions, we can differentiate against the entire class. For example, in this case, your descriptor was symmetric functions, and it had something like 90 parameters. And if I call the function parameter gradient, I will just get a dictionary back in Python, which contains all the derivatives against every field that is of double precision, basically floating point numbers, and it will return you a dictionary with those particular fields and what their derivatives are. It's actually really, really useful if you are doing some sort of your like uncertainty analysis or sensitivity analysis, because till now, not that many people have done that kind of work with descriptors. They just take a descriptor, oh, see, it follows these symmetries, and they're done with it. But now we are actually working on having a more thorough analysis of all of these descriptors to see which particular parameter really matters, which particular parameter you should really tune. So finally, what we got out of Enzyme, first thing was it was really high performance gradients, and the second part was those gradients were correct, because one of the descriptors that we were using is called bispectrum, and it turned out after I guess 3 years of it being used that it only gives accurate gradients up to single precision. If you go in full double precision, your gradients actually start to deviate from the correct gradients. It is not a problem if you are computing forces, because there will be some numerical noise and you can get away with it. But when you are trying to do these kind of your uncertainty analysis, then it becomes really difficult, because that noise means your descriptor will not follow certain symmetries that you expect it to follow. For example, if you will try to take its eigenvalues, you expect certain degenerate zeros that should be there based on symmetries, but they will not be there because the descriptor is noisy. Whereas when I basically took the same C++ code and copy pasted it in my library and ran it with Enzyme, and it just worked, and the derivatives were completely correct. So this was the biggest aha moment that we had, just the entire year of that I was wasting on this thing finally paid off. This is the use case that we want to go through. It has uniform API. You can use through Python, you can use C++, and it all works. It is really easy to extend and maintain. For example, this is one of the forward function that is used, one of the descriptors called SOAP. It's basically like an integral over some radial function. And what people usually do is they always take this Rn function to be some sort of Gaussian, etc., because then the whole equation becomes analytically solvable and they can compute its gradient. But now with Enzyme, we can pick almost any arbitrary Rn and we can switch it to numerical integration, and we know this works out of the box. We tried with simple your polynomial functions, because for them, people have shown that numerical integration of SOAP works, and we get exactly the same values. This also enabled us with rapid prototyping. We wanted to compute derivatives not against the positions, but against the distances, so that we can calculate something called your Piola stress. And in normal cases, it would have been I guess, a week's work where we had to recalculate all the derivatives against the positions and see how exactly we can implement them again and rewrite everything, all the gradients, etc. But in this case, all we needed was, instead of taking distances as an input, instead of taking coordinates as an input, I just edited the function slightly so it takes distances and work on it, and we got the gradients correctly out of that one. So, and libdescriptor comes with support for PyTorch autograd. It basically takes the Enzyme function and wraps them in your autograd functional object in Python, so that it can, on Python side, it can directly, your Python autograd gradients can directly flow through them. And it also has batching support, which is something rather limited that we have not seen in other libraries. Because Enzyme supports mutating code, we can give it we can concatenate 5 or 6 different configurations with each neighbor pointing appropriately, and it just works out of the box. It will work with all of them in single one. What challenges we faced? The biggest issue that comes up again and again with Enzyme is that installation is not as straightforward as just giving a make command. You first have to install Enzyme, and then it is as easy to install as Enzyme is. On most systems, for example, on my laptop, it's 5 minutes job. But when we were installing it on your Lawrence Livermore system, which was a Power PC, it took us 1 week to figure out. And the final solution was basically run the cmake command with your GNU compilers, where it will fail, but it will cache the tool chain. So then you can run with the proper compilers, and somehow that worked. And that is our workflow there, that you run first, let it fail, and then you let it run in that case. Second is distribution, how suppose even if I do compile that code, how will I distribute to different users? I cannot give them source because again, they have to install Enzyme for that one, although they don't need it for runtime because the binary is already there. So current solution that we have that I came up with was from a generous help from ChatGPT is to basically put all the binaries in a single distribution that includes my own glibc, my own libstdc++, and just ship it across so that it works on everyone's PC. It works, but it only works for Intel because it only works for x86 because that's the only laptop I have. After MacBook, I guess I will have binaries for MacBook, etc. as well. And it has limited this is not related to Enzyme, but most like our own this thing, that it has only CPU support because that's the only thing that we have written it in. We are waiting for, we saw the thread on GitHub about Cocos support. Once that works, then we will start porting it to GPU because a lot of our code, you actually use that one, and then we can make it all of those. Certain things were a bit surprising. For example, it fails, Enzyme sometimes fails in standard template libraries, especially like if it has a lot of your templated code. For example, the cylindrical Bessel functions that I used, it works if I give it like in a single file, I ask, oh, this is a standard, your Bessel function, can you differentiate it? Enzyme works fine with it. But when I add it in my own library, there is some cascading type, type analysis failure where it just refuses. However, if I just take that code and remove all the templates and just define it as double, it again works. So I guess it's just hit or miss kind of things. And this is actually one kind of minor issue that a lot of times, a lot of basic functions we have to rewrite ourselves so that it actually works with Enzyme because it's just less headache that way rather than figuring out where exactly things went wrong. Okay, and lastly, it is like a mishmash of C and C++ kind of paradigm because in my experience, Enzyme works way more efficiently if you give your code in like a C kind of plain your notation, just pass the pointers along and it will work fine. If you get too fancy with C++, your mileage may vary. And finally, I think I would like to say that it would be really nice if there's like a Conda package for Enzyme because it would make everyone's life a lot easier. We can ship a lot of different binaries, etc. And if anyone is willing on a Conda package, I can volunteer like 4 hours per week of my own time. You will have like an intermediate level user which you can guide and I'll work whatever you want for that thing too. Mostly because it's really, really becoming integrated in our workflow. We are having more and more projects where we are using Enzyme, so it will benefit us a lot. I did try making a Conda package for Enzyme, but the problem was not Enzyme. Problem is LLVM, and there are no good Conda package for LLVM. If you install like CLang, you will not get the CMake files with LLVM. If you install libLLVM, you will not get some compilers, etc. If you install both, there is like mismatch of version, etc. So that became like a huge help. So you have to start with Conda. But like I said, I'm more than willing to volunteer my time if somebody is like willing to guide. So like to summarize, what we have currently, we have four different your descriptors implemented. We have Bayer symmetry functions, bispectrum, smooth overlap of atomic orbitals, which is like the most popular one most people use, and a descriptor called chi, which is something internal to Lawrence Livermore lab. They just wanted it there. Currently, I'm working on the most advanced version of it, which is called atomic cluster expansion, which is also one of the most powerful one. And although this is like we discuss everything in terms of our own training framework called Clay for OpenKim, this is not limited to that one. It's basically like a generic library, and you can use it. For all x86 platforms, installation is as simple as pip install live descriptor, and it will work. These are the documentation and GitHub links if anyone is interested. And yeah, so what are the future directions that we are looking for? First thing would be to implement efficient Jacobians and Hessians for our descriptor functions. So currently for Jacobians, I'm using the same, basically run the loop n times with your one hot vector kind of thing. I'm not sure whether there's any efficient method other than that. And for Hessians, I have to still figure out how to implement the forward diff in this one. Because when I tried giving just replacing your underscore, your auto diff function with forward diff, it compiles, but I get always all zeros. So I'm not sure what is going wrong. So I have to figure that one out. Most of these problems are trivially parallelizable because in your configuration, suppose if you have n atoms, you can calculate for all of those atoms in parallel. Currently, it does not do that. Currently, it's a for loop, but I have to implement OpenMP support for that one. The reason why OpenMP support is not there is because then when I will package it in Python, I have to add additional libraries, libpthread, and all those, and it was okay, fine, let's keep it simple for now. Then there's GPU support. That will take a long while because currently it's not on our horizons, yes. We also have like a semi-working package called Torch SCF, which is for Torch self-consistent field, which basically implements your simple Hartree-Fock method and uses enzyme to differentiate it rather than analytical derivatives. The reason for that is because then we can use it for different kind of things such as your optimization and integrating this whole thing into PyTorch kind of level, layers. It's basically like a first principle code with some minimal DFT and Hartree-Fock that you can use for machine learning. And we will have basically JAX wrappers for it. It's still work in progress because JAX does not have mutating support. And finally come up with XLA backend for the whole thing. And I will get to it as soon as I can figure out how to work the Bezel thing out because I can't compile with Bezel, I'm sorry. And like the Moonshot project, just it works. Why not just give entire Kim API and let it deal with it, let the enzyme differentiate through everything that is there. We are still discussing, but I think within 1 year we might actually see that. And I guess that's pretty much it. Rest are just results, but these are not for your enzymes. So they were just for graph neural networks that we have implemented, and we have implemented it in parallel. So yeah, I guess that's pretty much it.
Thank you. Any questions? Any comments?
I have 2 questions, or 1 question and 1 comment. Do you still have the Psycho Julia code around that you tried?
Yes, it should.
Because it would be interesting to see the performance comparison between Enzyme C++ and Enzyme Julia.
No, okay, yeah, it is there, yes. I can
so we should take a look at that. And I think like the distribution problem is a real one. I think probably for C++, spec is the closest thing.
We also have Homebrew. So if you're a Mac person,
well, you know, Homebrew is Homebrew.
Yeah.
The only thing I could offer in that regard is we have pre-built binaries through the Julia binary builder for Enzyme.
Okay.
For LibEnzyme. So that could lead inspiration for Conda support. But
so is it available? How many platforms is it available for?
All of them.
Oh, great.
Windows, Linux, Mac, PowerPC, ARM. I think the only thing we're not supporting might be Windows 32-bit.
I didn't care about Windows.
Yeah, but we should figure, I mean, this mainly comes down to, we should find someone who knows Conda, because there is at least some LVM package. I actually even remember years ago, I packaged Taper, which is a fork of LVM, during tensor comprehensions on Conda for no reason. So it should be possible. It's just been so long that my knowledge of how Conda inside works is...
Yeah, but I mean, one of the biggest appeals of the enzyme.jl support, the Julia enzyme version, is that it just works with package manager.
So does it also come with all the necessary compilers and stuff?
Those would be a little bit iffy, because there's like, it's the Julia version of LVM, which we don't validate for C++ support, but in theory it does.
Okay.
It's just no support from our side.
We have people who knows Conda a bit, but for most packages it is quite straightforward. The problem comes if it's a compiler-based package. Yeah. Basically, if it's a compiler, then Conda has a lot of different issues that you have to jump through and all those kind of things. So, like I said, the biggest problem is not enzyme. If I have a working LLVM environment, enzyme should be really straightforward. Biggest problem is to get a coherent LLVM package. So, if you can push them to push a Conda package, that would actually be a much better solution.
Other questions?
I know OpenMN has support for integrating PyTorch neural network potentials, so I don't know how your stuff you presented at the start compares to the OpenMN model.
Which model?
OpenMN.
Oh, so currently we don't have any support for OpenMN. I am actually working on it to basically add. It is not that difficult. It's just that we haven't gotten around it. And second, the biggest reason for no OpenMN support is that for some reason it is not there in your materials community. They mostly prefer LAMPs, so LAMPs is our always main focus. But I actually like the OpenMM more, so I am working like one bit on the side. So currently there is no OpenMM support.
Other questions, comments? If not, let's thank Nate again.
Thank you.
And with
This is not being presented. This is just me to remember weird statistics I looked up. Okay, so first of all, I want to just apologize to Valentine for clapping again into the microphone. I want to thank everyone who's spent countless hours to make this meeting possible. Organizers, presenters, and attendees who've really made this a great conference, apparently including, in spite of AV logistics, more than 300 people who joined the live stream at some point, which is kind of fun. Also, more generally, want to thank the entire Enzyme community who've been doing so many amazing things as users, builders, etc. I quickly, over the background, and I'm going to forget these numbers, which is why I brought a computer with them written down, looked up some quick stats since roughly last year's EnzymeCon a year ago. In the past year, we've had more than 1,000 commits to different enzyme repositories, more than 11,000 unique visitors to the various enzyme web pages, and the Julia bindings, which, as package managers exist, have the ability to look up how many people downloaded it. It's hard to do that from GitHub clones or like various other ways people have installed it, but have been downloaded more than 29,000 times. We've had a lot of really fantastic work, some of which we got to see here, some of which unfortunately wasn't presented here, but I heavily encourage looking into the various GitHub orgs and just talking to people who've been doing interesting things. But examples include, of course, sparsity, more legible C++ error messages, climate models, IPUs, finite element methods, to name just a few. Overall, thank you guys so much for coming, and see you at EnzymeCon 2025.